I have a Markov chain where the transition probability matrix, which is always stochastic, has the additional property that the column sum is also 1. When that such a thing happens, what do you call such a matrix? It's a doubly stochastic matrix. Suppose you have a transition probability matrix which is doubly stochastic. Then what do you know about its stationary initial distribution? So it's all same, you know that, okay? So in particular, if I have a 2 by 2 doubly stochastic matrix, no matter what the entries are, it's always half-half. The stationary distribution or invariant distribution is half-half, okay? Now, can I use this coin to create a transition probability matrix and create a Markov chain that has doubly stochastic transition probability matrix? So essentially, I'll be creating a sequence of 0 and 1, just like the first example that I gave at the beginning today. And if I denote the sequence as x1, x2, xn, I'm trying to get a Markov chain with doubly stochastic transition probability matrix, and then automatically the xn will converge to the probability distribution that puts mass half and half on 0 and 1, right? That's equivalent to tossing a fair coin. That's equivalent to making a fair selection between two people. So I have to run the Markov chain long enough, and then I'll have to stop. And whatever the outcome is, if it is 0, I choose one person. If it is 1, I choose the other person. That's the strategy. So it will be approximately fair choice, right? But in the limit, I'll get that, okay? But how do I create such a transition probability matrix using my coin? The coin has some probability of turning head and some probability of turning tail, right? Let's say the probability of turning head is P and probability of turning tail is 1 minus P. So I take as my first row what? P, 1 minus P. I should take as my second row 1 minus P and P. How do I use the coin to generate the Markov chain now? So if I want to generate the Markov chain with such a transition probability matrix, so my transition probability matrix is now P, 1 minus P, 1 minus P, P. And this P is strictly between 0 and 1, okay? My coin may not be fair, but it should not be completely loaded, okay? So how do I use my coin to make a selection? Or rather to generate the Markov chain first. And then in the limit, the Markov chain will give me the selection. Yes? So what does it represent? Say the states are 0 and 1. States are 0 and 1. This is the transition probability from 0 to 0. This is the transition probability from 0 to 1. And it is the transition probabilities that you need to generate the Markov chain, right? So tell me, how would you generate the Markov chain? So suppose I start with the state 0. Say I choose one person. That's my initial choice. That's not my final selection. I choose one person. Then I will be tossing the coin. What will happen? It will be giving me either head or tail. Suppose head is represented by 0, tail is represented by 1. If it is head, then I keep the same person. If it is tail, I switch to the other person. If I had chosen the other person, then I toss the coin and then it is exactly the opposite thing. Okay? And then I keep on tossing the coin and I keep on changing or retaining the same person. So I go on doing this for a long enough time, and in the limit, I'll make a fair selection. Now there is a difference between this approach and the simple approach that you gave me earlier, which is based on two tosses, head, tail, tail, head. What is the difference? There, once you make the selection, it is exactly fair. Whereas it is only fair only in the limit, and here you may have to toss it several times. There also you may have to toss it several times because you may not get head and tail in the first go. So for choosing between two people, it's not a very useful thing, okay? But it becomes very useful when you have to choose from a large number of people. And suppose you have some random mechanism to choose randomly from n objects, but you do not know what are the probabilities of selection. Then you can create a transition probability matrix and run the Markov chain long enough. Okay. How do you create the transition probability matrix in that case? When suppose I have a probability distribution P1, P2, say Ps, and S is large, say. So all these Pi's are positive, and summation Pi is equal to 1. Somehow I can generate from there, but I don't know what these Pi's are. Suppose, but I have a way to generate that. It could be something like this. Suppose S is 6, and I have a die. I don't know what are the probabilities of turning each face, but I can roll the die and look at the face. Okay? Now the chance for 1 may be P1, chance for 2 may be P2, and I don't know exactly what the chances are. I only have the die, and it may not be fair. So it's a situation like this. I have a device that can help me to generate from this probability distribution. So I start from something, and then how do I create my transition probability matrix? That will be doubly stochastic. How do I create it? Following the same idea that I had there. So I can take these Pi's as the first row. What should be my second row, third row, like that? Huh? So what kind of matrix is that? When you, it's a symmetric matrix. Well, how are you creating this particular symmetric matrix? So you have these Pi's, and then what you have done is that you have just like rolled it a little. You have brought P2 in the first place and taken P1 in the last place, right? And when you do that, what kind of matrix you get? What is it called? Anybody knows the name of this matrix? Where these rows are like cycling? Circulant. It's a circulant matrix. Okay, so you can create a circulant matrix which will be doubly stochastic. And then you can have the uniform distribution or fair selection from any set of individuals. So Markov chain can generate uniform distribution on an arbitrary set like this, starting from a distribution which is not known to you. When I had the die, I knew that there are these probabilities, but I didn't know what are the values. So I'll be rolling the die. If the die gives me 2, I started with something. So suppose I have 6 people, okay? So I started with 1 person. Then I will be rolling the die. If it is giving me 1, I retain the same person. If it is giving me 3, then I take the third person. Then I will be rolling the die again. And then I will go to the third row and look at what I am getting there. Okay? So do you understand how this thing can be used? So you see one very simple and powerful application already, that uniform distribution on any set can be generated in limit by this result. Okay? This approach, this is what is called Markov chain Monte Carlo, where you want to generate from a particular distribution like the equal probability or uniform distribution, but you don't have an easy way of doing that based on the devices or resources available to you. But you can generate from some distribution which is convenient for you. What you do is you create a Markov chain using the devices or resources available to you to generate in the limit the distribution that you want to generate eventually. And the simplest application is the one that I have just said. Now, how do I generate any distribution using this idea? But before that, let me give you a very important concept.